what I want to do is just finish up on the atom, and just have a little addendum here, and then we'll press on to the next topic. So page 35, we see particles and their average radii, and I just wanted to lay this out to you so you could kind of get a feel for the comparative sizes that are in play here. So we're just going to walk down the list. At the top of the page, you see a little chart here with particle and the approximate radius of that particle. So we'll start with molecules. Okay, molecules on average have a radius of roughly 10 to the negative 9 meters. All right, so that's really weeny and tiny. So that would be, just so you can see it, that would be 1, 2, 3, 4, 5, 6, 7, 8, and a 1 meters, okay? A billionth of a meter. Now, molecules come in different sizes. Yes, they do, that is true. DNA molecule is huge, that's true. But on average, when we're talking about, you know, the more simple molecules like CO2 or water and so forth, on average, the radius is somewhere in the neighborhood of 10 to the negative 9 meters. Then, below that, atoms. Atoms, on average, have a radius of 10 to the negative 10 meters. Then, the nucleus. It will range from 10 to the negative 15 to 10 to the negative 14 meters. Now, I want to pause here and do a little comparison. We're just going to use some, we'll use some of our arithmetic. So, for an atom, we want to say is somewhere in the neighborhood of 10 to the negative 10 meters. And a nucleus, we'll say 10 to the negative 15 meters. Okay, so now let's look at what the difference is between these two sizes. To get from here to here, you'd have to multiply by 10 to the 5th. Or in other words, 100,000. So what we're saying here is that on average, an atom is roughly 100,000 times the size of its nucleus. That's how small the nucleus is in an atom. If I was to draw an atom more accurately, and we'll use our old friend, the hydrogen atom, even if I made the nucleus that big in my drawing, that would be too big. In actual fact, if I drew the atom to this size, the nucleus would be too small for you to see. It would be microscopic. If you took a hydrogen atom and blew it up so that the single proton in its nucleus was the size of a pencil eraser, we'll say, the electron would be over 100 feet away. Another way to think about it is this. If we blew up a single hydrogen atom so that that proton in its nucleus was the size of the sun, the electron would be 4 times the distance to Pluto. That's how much empty space there is in an atom. In other words, what we're saying is, by comparison, by ratio, a single atom has a higher percentage of empty space in it than the solar system does. That's what you are made of. Moving on. So then we get to the nucleus, which after the nucleus comes protons and neutrons. Okay, have a radius of 10 to the negative 15 meters, and then below that there's a particle we haven't talked about yet, quarks. It turns out that protons and neutrons are made of even smaller pieces and parts. They have an average radius of 10 to the negative 18 meters. So in other words, to jump from 10 to the negative 15 to jump to 10 to the negative 18, that means that quarks are 1/1000th the size of a proton or a neutron. What are quarks? Well, there are 6 basic types of quarks. They're called up, down, top, bottom, charm, and strange. A proton is made out of 2 up particles and 1 down particle. A neutron is made out of 2 down particles and 1 up particle. So yeah, even smaller bits and pieces. So that's just kind of to put a capstone on our look at how an atom is put together. All right, now we'll move on to page 36. More history, how we got there. We're going to look at some hysterical figures. At the top of the page, there is that quote by my favorite author in the world, Robert Heinlein. He said that the three-legged stool of understanding is held up by history, languages, and mathematics. Equipped with these three, you can learn anything you want to learn. But if you lack any one of them, you are just another ignorant peasant with dung on your boots. Now, that is rather harsh, I'll grant you. But you know, there's a kernel of truth in there. We do need to know history. We need to know how we got here. And you'll find, this is one of the things that I find fascinating, is that even today, in this 21st century, stuff from ancient times is still in play today. So this is not to turn this into a history course. I'm just going to do some rough outlines here. For those of you who are history geeks, you'll see that I'm going to cut some corners here. That's all right. I just want you to get the gist of this. So we'll start with this fellow right here, Aristotle. Okay, so we're going to put him at roughly 500 BC, give or take a century. And we don't need this here anymore. And I'm just going to put out some rough factoids here, and then we'll flesh them out. So, number one, you may not see it written in so many words, but we can certainly make the case for this one. We can call him the father of scientific reasoning. Not the scientific method. Don't confuse the two. That comes much, much later. Okay? 2. He was a Pythagorean. Which is to say that he subscribed to the Pythagorean philosophy. Now, you may remember Pythagoras from your high school math classes, the Pythagorean theorem. A squared plus B squared equals C squared. Okay. Yeah, same guy. He was a teacher, and so if he was a teacher, well, that meant he had to have students, and perhaps his most famous student tutored Alexander the Great. Fact. Well, if he's a teacher, that means he had a curriculum. Here is his curriculum. Here's a piece of his curriculum. He taught the geocentric system, which is to say the idea that the Earth was the center of the universe. Now, a little bit about Pythagoras and the Pythagorean idea. The Pythagorean thought was this. So, let me flesh this out. This Pythagorean idea, this Pythagorean thought that anything observed in the natural world can be explained by careful observation, logical inference, and deduction. Let me clear up a common confusion point on an inference. If I imply something, you infer its meaning. Okay. Which is a good start. It's incomplete, but it's a good start. We're talking about the five senses, using the five senses, all right? Sight, hearing, touch, taste, smell. That's it. That's what we got. All right, so Aristotle is a Pythagorean. And this is at a time when culture is just exploding in ancient Greece. This is before Greece is a country as such. You have a bunch of these city-states, but there's all sorts of stuff going on. I mean, there's explosions in philosophy, in mathematics, in the arts, in architecture. But we need to be clear, as advanced as they were for their times, it's important to keep them in the context of their times. Technology, yeah, not so much. Plumbing, very, very limited for the rich folks, and then for the rest, no, not even that. And the important part to keep in mind, and you'll see why. One of the things that has yet to be invented in this time are optics. Optics have not been invented. All right? So what that means is we have to put this in the context of it. You know, medicine doesn't exist as we understand medicine. So what that means is if you were transported back to that time, this is for those of you who wear glasses or contact lenses, because no, you don't want anybody to know that you have to wear glasses. You know who you are. Do you know what you would have been back then? You'd have been blind. You'd have been squatting on the sidewalk with a bowl going, "Alms for the blind." That's what would have happened. If you know somebody, or you know somebody who ever had their appendix out, what would have happened to those folks? They'd have died. Okay, so this is the times in which they live. Still, there's this explosion of philosophy and the arts and mathematics. If you took a geometry course in high school, your textbook is a direct descendant of a book that was written back then by a fellow, you may have heard of him, named Euclid. Euclidean geometry. All right, and any geometry text you pick up is a direct descendant of that book. It is still being published to this day. Euclid's Elements is what it's called. It is the longest continually published text in human history. If you watch TV, Or you go to the movies and you watch stories. You like watching, adventures or science fiction or what have you. That is a direct descendant of theater as we understand theater to be. Back then, they invented theater as we understand theater. Okay, another sea story. My last overseas tour was in Sicily. And at one point, Greek influence extended out as far as Sicily. So when I was over there, I would frequently rent a little Fiat on the weekends and just go bimbling around the countryside and visit these little towns. And I was in this little town, I'm damned if I can remember the name of it, a little small town where they had restored an ancient Greek amphitheater. And they were staging one of the ancient Greek plays. And so, yeah, it was this amphitheater with like stone benches in a circle looking down on a stage. And I stopped and I watched this play. And it was being done in ancient Greek. I couldn't understand what was being said, but I didn't really need to. Boys and girls, let me tell you, the 20th century did not invent X-rated. No, they did not. I was watching this play, and I'm here to tell you, I'm a sailor, and I was blushing. So, yeah, this is where so much of what we take for granted comes from. Now, he was a teacher, and he tutored Alexander the Great. Again, this is back in the time when there were city-states. There was not a country called Greece per se. There was a culture of Greece, but not a country as such. And so you couldn't swing a cat without hitting somebody who wasn't a prince or a king or some type of royalty. Well, one of them, King or Prince Philip, wanted his son to get the best possible education available. It would be like the Queen of England sending one of her grandchildren to be tutored by Stephen Hawking, that sort of deal. So Prince Philip sent his son to be educated by Aristotle, and that gives us Alexander the Great, considered by many to be the first truly modern, educated military leader. And his accomplishments speak for themselves. So much so that even today, in places like West Point, you may have heard of, they still study the campaigns of Alexander to this day. It's part of the curriculum. The guy was brilliant. Now, to this geocentric system, where's that coming from? Well, again, this goes to the Pythagorean idea of being careful in your observations and being kind of hard-boiled about it. So if I asked you, what did you see this morning when you looked in the east? You would probably say, well, I saw the sun come up. Well, did you really? And the answer is obviously no. The earth is turning, and hence the sun appears to come up in the east. We know that because we got taught that back in grade school. But if you did not have the convenience and advantage of telescopes with which to do astronomical observations, how do you do astronomy then? Well, Mark 1 mod 0 eyeball. That's the only way they do astronomy back in those days. So Aristotle and so many like him are saying, what is it we can, excuse me, what is it we can absolutely swear to? What can we swear to in a court of law, if you want to put it that way? Well, what I observed was the apparent motion of the sun coming up. And in the evening, I saw the apparent motion of the moon coming up and the stars. Well, could you not infer that the earth was moving? Well, you could, but could you detect any movement? No. Even though, if you do a little back of the envelope arithmetic, it turns out here at roughly 45 degrees north latitude, where we are here in Maine, we're spinning around at roughly 700 miles an hour right now. But you can't feel it. You can't feel that motion. So there's nothing in your five senses that's telling you that you are in motion. Nothing. And so just stripping it down to the barest elements, the only logical conclusion you could draw from it is that the sun is apparently moving, and so are the stars, and so is the moon. Well, okay, fair enough. Fair enough. He had some other interesting ideas, Aristotle did. One of them was that if you threw a ball through the air like so. He said that the air would come around like so. Oh yeah, it does. But not only that, it would come around like this and give the ball a little bit of an extra push. You know, that kind of sort of makes sense, but no, that's not what happens at all. But that's what Aristotle thought. He also believed that heavier objects fall faster than lighter objects. So here's an experiment you can do at home. Grab yourself a rock or any object and a piece of paper. And just go ahead and drop them side by each. And lo and behold, just as Aristotle predicted, the rock fell faster than the piece of paper. But here's what I want you to do. Grab that same piece of paper, crumple it up into as tight a little ball as you can, and repeat the experiment. And now drop them like so. And lo and behold, they arrive at the same time. You didn't change the weight of the paper at all. It's still the same weight. Well, what happened? Well, air resistance. And believe it or not, it took over 2,000 years for mankind to figure that one out when we encountered an arrogant smartass by the name of Galileo. We'll get to him later. So, oh, and also, here's another thing that Aristotle asserted. Back then, we did not have chemistry as such. We had the four elements, you know, earth, wind, fire, water, okay? So, this rock is of the earth, and why does it drop? Well, we know it's because of gravity, but Aristotle's explanation for why the rock drops when we let it go like that, well, it's because the rock is of the earth and it wants to return to where it came from. That was Aristotle's idea. But let's cut him some slack. You know, he did pretty good with what he had to work with. Now, again to this idea of a geocentric system. If he had just stopped right there with using this Pythagorean approach to explain the apparent motion of the heavens, well, okay, you can see that. But then he went one step further. He said, it is axiomatic, which is to say, it is self-evident, it is axiomatic that mankind is God's greatest creation. And logic would therefore dictate that God would not put his greatest creation in any place but the center of the universe. And so at this point, Aristotle is invoking deity as a scientific rationale, what we would call a scientific rationale. But before you get too up in arms about this, you have to also understand this is of the times in which it doesn't matter what your discipline is, whether it's poetry or writing plays or mathematics or architecture or philosophy. Everything went into one big bucket called philosophy, and that would include even theology. It was all fair game. It was all, there was no distinction made between the different disciplines. It all came under one big heading called philosophy. And so you see there at the bottom of the page, there's the idea of the Earth-centric or geocentric universe, and you can see Earth, Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Well, what about the rest of the planets? Well, you can't see the other planets with an unaided naked eye. Uranus, Neptune, and Pluto, those came later with the advent of the telescope. Okay, so that's page 36. Moving on to page 37. All right, Ptolemy. All right, he is a Greek Egyptian, Roman astronomer. And this is roughly 200 AD. First name Claudius. All right. So what's this Greek, Egyptian, Roman stuff? Okay. Well, we're 200 AD. The Roman Empire has spread throughout the region, including both sides of the Mediterranean. And in a nutshell, he's a man who has essentially triple citizenship. His parents are Greek and Egyptian. I can't recall whether it's his dad who's Greek, mother's Egyptian, or the other way around. But they're all subject to, subjects of the Roman Empire. So hence this multiple nationality here. And it's not all that unusual. Here in Maine, we have any number of folks who have relatives who have dual citizenship in both Canada and the United States. So yeah, okay, fair enough. He's an astronomer in 200 AD, roughly 200 AD, and we do not yet have telescopes. Telescopes aren't here yet. So how does Ptolemy do astronomy? Well, they use a contraption that looks kind of like a ship's sextant, and they sight stars through these long tubes. So imagine taking a drinking straw, closing one eye, and trying to line up a star through a drinking straw. That's some painstaking work. They did it. They did it. So what about Ptolemy? It's this. He created the most comprehensive most comprehensive geocentric model ever. This was exquisite. It was his life's work. Now I have to pause here and do a little side trip to explain something. The word planet is derived from an ancient Greek word that means wanderer. Okay. Why? Well, I'm going to invent a fictitious constellation of stars. We'll call it the Pentagon. So you go out one night to do some stargazing, and you see, we'll say today is the 25th, yeah. So today's the 25th. And you spot the planet Mars right there. You go out a week later to, we'll say, the 2nd of October, and Mars has moved over here. And then you go a week later to the 9th of October, and Mars has kind of doubled back over here. One more week later, Mars has continued on its way in the original direction. What's going on here? That's called retrograde motion, by the way. So what is going on? Well, let me explain to you the true reason that this happens. So here's the sun. Here's the Earth. We'll put the Earth right here. And here's Mars. Put him right up here. Okay. And they are orbiting the sun like so. All right. So what happens is this. Earth is closer to the sun than Mars, and so Earth is going to orbit faster around the sun. It's going to actually have a higher speed than a more distant planet. And as time goes on, the Earth will overtake Mars, as you can see here. And a way to think about that is, imagine you're on the highway and you're traveling at 70 miles per hour, got the cruise control on, and you pass a guy going in the same direction who's doing 65. But relative to you, that car seems to be going backwards relative to you. That's what's happening here. We're passing Mars, and so it appears to be kind of doubling back relative to us, just like if you pass a car. That's what causes this retrograde motion against the backdrop of stars. Well, that means that you would have to understand how orbits work. They did not know that then. Remember, there's no telescopes, there's only the Mark I Mod 0 eyeball and the 5 senses. So how does Ptolemy explain this retrograde motion? Well, you see a chart here showing Ptolemy's model of the universe, and what he's saying is as these objects go around the Earth, we'll say Mars, for instance. Not only is Mars moving around the Earth like so, but it's also doing this little loop-de-loop. It's called an epicycle. So what are epicycles? Well, they are loop-to-loop movements. Of planets. Well, what's holding them all in place? Well, as we know, it's gravity that holds the planets in place as they orbit. But they did not know that then. They had not yet made the connection between the gravity that we experience on the surface of the Earth and the gravity that makes planets do what they do. That didn't come until much, much later. So what holds them in place? Well, and they don't call them orbits. They call them deferens. They were the pathways of the objects. And what held them in place? Crystal spheres. Crystal spheres were the physical structures holding these celestial objects in place. Think of them like, have you ever seen those Russian nesting dolls? You pull apart and there's another little doll inside, you pull it apart and there's another little doll inside, and so on. Or some of you remember the Cat in the Hat, with the cat, multiple cats underneath each hat. It's sort of like that. So that's what they believed held everything in place. Now, it's easy to snicker here in the light of the 21st century, but what you need to understand here is that Ptolemy's model was absolutely exquisite. And it was a triumph, and it is still considered to this day a triumph of human thought. Why? Because it explained everything that could be observed beautifully. It would predict lunar eclipses accurately. It worked. It had, by the time Ptolemy died, it had over 80 moving parts. And that's important to remember. It had over 80 moving parts. And like I said, it was exquisite. Just beautiful, beautiful. It was wrong, but we didn't know that then. And we had no way of knowing that then. It worked. And on the page here, you'll see an illustration of Ptolemy's model of the universe, as well as an illustration of how the crystal spheres were laid out. Well, page 38. I'm going to jump ahead roughly 1,200 years. Copernicus. Okay, that puts us in the 14 to 1500s. Some factoids. Polish church deacon and an astronomer. First comprehensive heliocentric model. Okay. So, Copernicus, a pretty interesting fellow, a profoundly well-educated man. Studied to be a doctor, traveled around Europe, going to different institutions, was fairly well-to-do, was a landowner and a landlord, and by all accounts, one of the most generous sorts of landlords you could hope for. He was always trying to help out his tenants when they hit hard times. Just an all-around good guy. He was also a church deacon. Some people have him as a church priest. You know, we can debate that one, but I think most accounts have him as a deacon. Point being is that he was, in some fashion or another, a church official, you know, steeped in church protocols and practice. And this is now, so now we're in the 14 to 1500s. The Roman Empire has come and gone. What is the predominant cultural force in Europe at this point? Well, it would be the Christian church. Now, I want to be careful about this. I don't want this to come across as church bashing, but we're just going to look at what the history is. So now we are in this point in European history where church is the predominant cultural force. But the influences of ancient Greece are still alive and well here. So we can just track this as it moves along. So first, we started out with Greek culture, Aristotle, Plato, Socrates, Euclid, Pythagoras, all of that. And then comes the Roman Empire. Now, the Roman Empire assimilated a lot of Greek culture. And so as a case in point, you know, Greek gods became Roman gods. So the Greek god Ares became the Roman god Mars. The Greek god Aphrodite became the Roman god Venus, and so forth. And so with that comes the contributions of the great Greek thinkers, you know, like Plato, like Socrates and Aristotle and Euclid and so forth. All right, so that's part and parcel now with Roman culture. After Rome falls and Christian culture, the church rises to preeminence, all of that knowledge also becomes part and parcel with church knowledge. And recall, we're coming out of what we call the Dark Ages. We're at a time where 99% of the people in Europe are illiterate. So who kept culture going? And this is where credit must be given where it's due. It was the church. It was the Vatican that preserved a lot of culture that otherwise would have been lost forever. So that means, yeah, Plato, Socrates, Euclid, and yeah, Aristotle is now part and parcel with church education. Church becomes part of church doctrine, because it so happens that there's any number of passages in Scripture that fit beautifully with an earth-centric view of the universe. So guess what? It now becomes church doctrine. Earth-centrism is now church doctrine. Copernicus, if anybody, would know this. Yet, he's looking at Ptolemy's model of the universe and he's saying, boy, that's got a lot of moving parts. Yes, it works, but there's got to be a simpler way. And he comes up with the heliocentric system with the sun, Mercury, Venus, Earth. And yeah, the moon does go around the Earth. Mars, Jupiter, Saturn, and then the stars. Look at that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Fewer than 10 moving parts in this model. And it works. It works just as well as Ptolemy's model. And so that gets us to a couple of ideas. Okay, quick review. Remember, we said that Ptolemy's model was comprehensive. And in this form, in either a math or a science form, when we say something is comprehensive, we mean that it explains everything. Okay? So, Ptolemy's model was comprehensive. It explained everything we could observe. The Copernican model is also comprehensive. It too can explain everything we can observe. But what there is to recommend the Copernican model is this. It's an important word you should know. The Copernican model is elegant. And in science, when we say something is elegant, we mean that it is simple and comprehensive. Both the Copernican model and Ptolemy's model were comprehensive, but Ptolemy's model was not simple. That gets us to this idea, Occam's razor. You should know what that is. Occam's razor. What Occam's razor says, and it's an overarching philosophy in science that we use to this very day, and this is important to know, especially in current times. It works this way. If you have two competing explanations for an observed phenomenon, and both of these explanations, however different they may be, are comprehensive, and therefore the only difference between the two explanations is that one is complicated and the other one is simple, you go with the simple one every time. Because that, boys and girls, is how science works. And this has been proven over and over and over and over again. So what is Occam's razor? Well, in cheap, sloppy language, it's this. The scientific application of the KISS principle. That is what Occam's razor is. Know that. What's KISS? Keep it simple, stupid. That's what Albert Einstein was all about. He was entirely about the KISS principle. And yeah, that's what Occam's razor is. In this time of COVID, it's important to know this. It doesn't take much imagination to get on social media and find any number of conspiracy theories that are out there. Be cautious. Be very, very cautious. 99.9999999% of these theories that you're going to uncover on social media will not pass that test. Will not pass that test. Okay. In order for them, just as a case in point, a lot of these conspiracy theories would have you believe that every scientist in the world is in on this conspiracy. Well, you know what? No, that's not how it works. It just doesn't. But just keep that in mind. It's important for us to understand what science is and what it is not. And that's a big, 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 big part of what science is. Now, this idea of the Copernican revolution. We live in the Copernican revolution today. Well, what is it? Well, it's that point at which mankind realized, sorry, we are not the center of the damned universe. And that upsets a lot of folks, but but that's why we call it the Copernican revolution. We give him the credit, not Galileo. Galileo comes later. Now, back to this idea. Copernicus knew that his ideas would go in direct conflict with church doctrine. He knew that. He was no dummy. And so he told his family, you know, shut up, don't tell anybody about this. Wrote a book, and his book was finally published, but he was on his deathbed. And the book was published literally the day before he died. So, you know, Copernicus is saying, you know, what are you going to do to me? Kill me? I'm dying. So that's how he kind of got away with it. He waited until the last possible minute to have his book published. So there's Copernicus. All right, we'll stop here and move on to another character.